The minimum size copper grounding electrode conductor required for a concrete encased electrode is 6 AWG. A concrete encased electrode, often referred to as a U for ground, is a grounding electrode encased in concrete. This type of grounding electrode is commonly used in new construction, particularly for buildings with concrete foundations. The National Electrical Code, or NEC, specifies the requirements for grounding electrode conductors, including the minimum size for different types of electrodes. According to the NEC, a concrete encased electrode must have a grounding electrode conductor that is at least 4 AWG copper. However, the size of the grounding electrode conductor isn't directly driven from NEC section 250.66, but rather from NEC section 250.68, which states that it shall be unspliced or reversibly spliced. That means you can use a split bolt or wire in a connector, and it needs to be continuous. The follow-up is NEC section 250.52 AFI, which describes concrete encased electrodes, which states that it shall be 4 AWG copper. Firstly, let's define the terms we are using. A grounding electrode is a conductor or group of conductors used to connect the electrical system to the earth. This connection provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. Secondly, a grounding electrode conductor, or GEC, is the conductor that connects the system's grounded conductor, typically the neutral, or the equipment grounding system, to the grounding electrode. The size of the GEC is determined by NEC table 250.66, based on the size of the unrounded conductors, or the service entrance conductors. Thirdly, a concrete encased electrode is defined as at least 20 feet of bare copper conductor not smaller than 4 AWG, encased in at least 2 inches of concrete and located within the concrete near the bottom of a foundation or a footing that is in direct contact with the earth. This type of electrode is very effective because of the large surface area in contact with the earth and the moisture-retentive properties of concrete. Now, why is the size of the grounding electrode conductor important? The grounding electrode conductor must be sized appropriately to safely carry fault current back to the source. If the conductor is too small, it may overheat and potentially cause a fire or other damage. The NEC provides specific guidelines for sizing grounding electrode conductors to ensure safety and reliability. The NEC specifies in section 250.66 that the size of the grounding electrode conductor for a concrete encased electrode must not be smaller than 6 AWG copper, while a 4 AWG conductor is required for the electrode itself as per section 250.52 A3. The conductor connecting it to the grounding bus or system must adhere to the sizing requirements based on the service entrance conductors, but never smaller than 6 AWG. The primary function of a grounding electrode system is to provide a lower impedance path for fault current to return to the source. This lower impedance path allows overcurrent protection devices, such as circuit breakers and fuses, to quickly trip and energize the faulted circuit, minimizing the risk of electrical shock and fire. The effectiveness of the grounding electrode system depends on several factors, including the type and size of the grounding electrode, the size and material of the grounding electrode conductor, and the soil conditions at the site. Proper installation and maintenance of the grounding electrode system are essential to ensure its continued effectiveness. Incorrectly sized or damaged grounding electrode conductors can significantly increase the impedance of the grounding path, reducing the effectiveness of the overcurrent protection devices and increasing the risk of electrical hazards. When installing a concrete encased electrode, it is important to ensure that the concrete is in direct contact with the earth. This direct contact is essential for providing a low impedance path to ground. The concrete should also be free of any additives or chemicals that could degrade the copper conductor over time. The NEC provides detailed requirements for the installation of concrete encased electrodes, including the depth and location of the electrode within the concrete. Adhering to these requirements is crucial for ensuring the effectiveness and longevity of the grounding electrode system. One common mistake is failing to properly bond the grounding electrode conductor to the concrete encased electrode. The connection must be made using an approved connector that is listed for direct burial. The connector should be installed in a manner that ensures a reliable and low impedance connection between the conductor and the electrode. Another common mistake is using the wrong size grounding electrode conductor. As mentioned earlier, the NEC specifies that the grounding electrode conductor for a concrete encased electrode must be at least 6 AWG copper. Using a smaller conductor can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. Regular inspection and maintenance of the grounding electrode system are essential for ensuring its continued effectiveness. The grounding electrode conductor and connections should be inspected periodically for signs of corrosion or damage. Any damaged or corroded component should be replaced immediately. The resistance of the grounding electrode system should also be tested periodically to ensure that it is within acceptable limits. High resistance can indicate a problem with the grounding electrode or conductor, which could compromise the effectiveness of the grounding system. In addition to concrete encased electrodes, there are several other types of grounding electrodes that are commonly used, including ground rods, ground plates, and metal underground water pipes. Each type of grounding electrode has its own advantages and disadvantages, and the best choice for a particular application depends on the soil conditions, the size and type of building, and other factors. Ground rods are typically made of copper or copper-clad steel and are driven into the ground to a depth of at least 8 feet. They are relatively inexpensive and easy to install grounding electrode option, but they may not be as effective as other types of electrodes in areas with poor soil conductivity. Ground plates are typically made of copper or zinc and are buried in the ground. They have a larger surface area than ground rods, which can make them more effective in areas with poor soil conductivity. However, they are more expensive and difficult to install than ground rods. Metal underground water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. However, the use of metal underground water pipes as grounding electrodes is becoming less common due to the increasing use of non-metallic water pipes. In addition to the requirements for grounding electrodes and grounding electrode conductors, the NEC also includes requirements for equipment grounding. Equipment grounding is the process of connecting the non-current carrying metal parts of electrical equipment to ground. This provides a low impedance path for fault current to return to the source, minimizing the risk of electrical shock. The equipment grounding conductor, or EG, is the conductor that connects the non-current carrying metal parts of electrical equipment to the grounding system. The size of the EGC is determined by NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. Proper grounding is essential for ensuring the safety and reliability of electrical systems. It is important to follow all applicable codes and standards when designing, installing, and maintaining grounding systems. Failure to do so can result in serious electrical hazards. The information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or contractor before making any decisions about grounding systems. This ensures that the system is designed and installed in accordance with all applicable codes and standards. Also, keep in mind that local codes and regulations may vary from the NEC, so it is important to check with the local authorities to ensure compliance. Staying up to date on the latest changes to the NEC and other relevant codes and standards is crucial for electrical professionals. This ensures that they are aware of the latest requirements for grounding and other electrical safety practices. There are many resources available for learning more about grounding, including textbooks, training courses, and online resources. Taking advantage of these resources can help electrical professionals improve their knowledge and skills in this important area. In conclusion, understanding the requirements for grounding electrode conductors, including the minimum size for concrete encased electrodes, is essential for ensuring the safety and reliability of electrical systems. By following the guidelines in the NEC and other applicable codes and standards, electrical professionals can help to minimize the risk of electrical shock and fire. Proper grounding practices are a cornerstone of electrical safety. It protects people and property from the dangers of electrical faults. The selection of the correct grounding electrode conductor size, especially for concrete-encased electrodes, is not merely a matter of code compliance but a critical safety measure. This knowledge ensures that electrical systems function safely and reliably.